recording is being in progress. So without any further ado, Famza, if you'd like to share your slides and give us your talk this afternoon, thank you.
Without wasting your time, I'll just move straight to slide 2. This is my topic, and as Stephen has said, I am a PhD researcher at the Department of Materials. Let me just move this to this side. Okay. This is the problem overview. I'm sure we can all see my slides. The problem that I've identified is that there is a problem with genes, especially for the pair and hourglass shapes. And this problem is more prevalent in South Africa, where I come from, because the African shape for many women, they have a narrower waist and a larger hip and bum. So the jeans that they buy, they tend to gape at the back waist, pulling the waist, pulling the waist, and they gape, I would say. And there's a reason why they're doing that. It's because the sizing systems in South Africa were based on the European and American sizing system. And they were adapted by fashion retailers, but they couldn't perfect the fit. And there is no one who was looking at, tackling the problem. They've tried, I must say, but because retailers are full of technologists and fashion designers, and this is a scientific problem to be solved. These are just newspapers that I found online, challenging the fashion industry. These are individuals challenging the fashion industry. Why clothing? For example, the first one is a UK one, Total Retail. That's a UK-based company, and you can see it's dated 12 March 2024. Try this on for size. Why US fashion retailers must not dismiss true sizing technology. The middle one is a UK-based one. The person who produced this, actually, this is a Guardian. It's an online newspaper, but the article was written by my supervisor, Dr. Simon Gill. And the last one is a South African online newspaper, News 24, where they are saying clothing sizes in SA are ridiculous. You can see that this is a global phenomenon. It's not just a problem that is South African. It's everywhere. And why women? Because women are caviar. That's why we have problems. We are not built as men. We are much caviar than men. So this is an illustration just to give you a background of a body shape I'm talking about. This is an hourglass. This is typical South African Black woman. And this problem is actually more prevalent on the Black South Africans more than other races. And the background is that we are descendants of Sachi Batman. I'm sure we're all familiar with that story, Sachi Batman's body shape that was, presented in France in some few years back. So because we are descendants of Sachi Batman, now we can think that sizings are coming from the British and American, and the sizing system were based on the ideal, body shape based on the European market and based on the American market. But now with the African market, we define ideal as someone who is this shape, the hourglass and pairs. Every woman will envy this woman. We all want to be, pear shape. That's why in Africa, you find a lot of cosmetic surgeries. People want bums, those who are flatter, because you still find that there are those who are not hourglass, who are straight, who are not pear shape. The difference between a pear and an hourglass is simple. Is the top part. Those who are hourglass, you find that they have fuller breasts, and those who are pear-shaped, they don't have breasts, but the bottom The bottom shape is the same. Narrower waist, larger hip line, a prominent bum. Due to this problem, there's a high return of clothing, you know, and the retailers are losing out, you know, and researchers now, like us, we want to be inclusive and we want everyone to feel that they are part of the problem by actually trying to solve this issue and develop a method that can be used by the fashion industry, not just me. It will be open for any retailer and any clothing manufacturer, you know, so that we solve this problem globally, because it's not just Africa and all this, I would say in the diaspora where there's a woman who is like this shape. And I've seen other races as well, like whites, they also have this race, that sort of this problem. Yeah, I've been, you know, observing in the malls here in the UK. I was shocked that this is not only for Black people. There are women who also look like this from other races. Now, this is really a problem that can be, sorry, I'm trying to, why is not moving now? Okay. Now, if you look at this is Kalaman. For example, the previous one, you see that there's this diagram. This diagram is an African. It's an African hourglass. There is a difference between an African hourglass and a Western hourglass. The African hourglass, you will see that there's a remarkable difference between the waist and the hip line and the bum. You can see the prominence of bum. Now, I want you guys to observe this versus the next slide, where now I will present the European or the Western hourglass. You will see the difference. This is the Western hourglass. You can see that the difference between the waist and the hip line and also the bump on the bum is not as remarkable, or it's not as prominent as the previous one. This is Western hourglass. This is where now the body shape, where the sizing system is based on. So which means now they excluded those who are extreme cases, like, you know, the African hourglass and pen. So in tackling this problem, I will use digital technology. Why digital technology? We've tried using traditional pattern making, traditional cutting, these traditional physical try-ons. And what I've discovered with that, number one, it's not sustainable. There's too much wastage there. So everything in the here and now with this research will be digital, where they will be measured using a 3D body scanner. And then from the 3D body scanner now to SIMD 2D, which is a digital pattern making software that is open, which is an open source. So we import the measurements now from the 3D body scanner and design a pattern now on this open source digital software called SIMD 2D. From this digital software, what we do now, we move to Claude 3D, which is now a fashion modeling software for virtual try-ons. So from this now, once the pattern is made or completed, I will then fit the pattern just to make sure that it fits on the wearer. But I will use now the virtual avatar. You know, in normal occasion, would you fit on human bodies, or we'll use the mannequins that we are all familiar in retail shops. But in this case, I will use a digital mannequin. For example, I've designed this trouser, I fit it on this avatar. I can see how the fabric flows on the body before trying it on a physical a human being, you know. So everything will be tackled here. Yes, we're still going to do random physical trials after we've tried on virtually. to see how the flow is, and then the movement, the comfort, all that. It will be detected now on Flow 3D. Okay, this is a methodology. Okay, I won't just go through it. I'll just move to the next slide. Okay, sorry. Okay, now the challenges this research aims to address. The body shape analysis is looking for better fit solutions through 3D scanning, as I said earlier, that will reduce waste from ill-fitting clothing that is readily available in the retail markets, on the retail outlets. And that's by promoting what sustainability. Now, the key measurements have been identified for this. Obviously, we are looking at the bottom part of the body for women. And then the pattern creation, we use technologies, all digital technologies, 3D scanning, as I said, the digital prototyping and simulation, you know, to improve accuracy and reduce physical samples, you know, aiding sustainable production. The last one will be integration. Integration, meaning we use body data in pattern making, enables customized on-demand production. We will just make the pattern for genes for a particular person. But in that particular person, you'll see that I've identified, I'm categorizing body shapes. Within the hourglass, you'll find that I will get 10 variations. And then whoever who fits in that variation, then we will code that size, that it belongs to this. Even on the pear shape, because they are different. So we will also code. This is what this research is all about. So, yeah. Sorry, I'm having issues here with my button to move to the second slide. Yes. Okay. This is what I've collected, you know, when I was going through research. And this is exciting because you'll find that in the 1950s, if you look at this, 1958, I've cycled that. 1958, the bust measurement was 31 inches. Waist was 23.5 inches. Hip was 32.5 inches. Of course, this is American because with the British, we use centimeters. In the 1970s, the same size 8, if you look at that measurement, the same size 8 is now, for bust, it was 32.5. For waist, it was 23.5, which is fine, still the same. And then hip, 34.5. Now you ask yourself, are we shifting or is the size shifting? What's going on? There's so much confusion around sizing and globally, garment sizing globally. In 1995, the same size 8, you know, the bust is 35. I don't know, maybe people are getting bigger. I have no idea. Because even if you look at the mannequins that are presented on this slide, you'll find that in 1958 and 1970, they were smaller. 1995 and 2012 were bigger. So which means we are getting bigger and bigger. Maybe it's because of the lifestyle that we, you know, we eat junk. I don't know. I'm not going to argue because I'm not a dietitian. But we are changing, and which means now as designers and fashion scientists, we have to study all these latest, you know, stats and adjust our sizing as such. 1995 compared to 1958, the bust now is 35 inch, the waist is 27, and the hip is 34. 2012, you can see again, we are getting bigger and bigger. Bust is 36, waist is 28, and hip is 39. So these are just, you know, irregularities that we found in the fashion garment sizing space. Now, limitations and future directions. Okay. There's cost and accessibility of 3D scanning tech. For example, in most countries, for example, in my country, we only have 3 body scanners that are located in 3 different universities. Already that is a limitation. Even if there are researchers who are, want to engage in this study, the facilities will be a problem, because if you want to capture the size, because this is not just about the size, it's also about the shape. If you want to capture using a traditional tape measure, it won't work. You need a 3D body scanner that will capture the shape of whatever human body, focusing on only specific body types, extreme shapes. Okay, skill gap in integrating advanced pattern tech. Future research, expand to more body shapes and apply it globally. Why I'm saying this is because this particular study is only focusing on the extreme shapes, which is hourglass and pear. There are other body shapes that other researchers can focus on, no, because those people are also having problems. For example, you'll find that there are women who are much bigger, the bust, the upper body is much bigger, and then the lower body, they are like a funnel. So we need researchers who will say, I want to focus on this particular body and develop a sizing system or whatever clothes that will fit this particular body shape, because I am focusing on this particular one. These are contributions to the fashion industry. I've touched based on that one earlier on, that the contribution to the industry is that I am creating a method that can be used by the fashion industry to develop garments that will fit them, but specifically for jeans in this case. So this is the cycle that I've created. Size stream, that's the first one, where we collect measurements, which is the 3D body scanner. We call it size stream in this university, located in my department here at the University of Manchester. Now from there, we move to Simly. So which means now from Simly 2D patterns, which is an open source digital pattern making software, where we import the 3D scan measurements from the SciStream 3D body scanner. From there, we move now to the 3D body scans avatar. So what we've done now, when I was measuring these guys from the 3D body scanner and importing the measurements from the 2D assembly, I was only dealing with measurements of the 3D body scanner. But now, on this particular one now, I am actually dealing with the body scans now, converting to avatars. And the same avatars that I'm using that were developed by the body scanner will now be used now for virtual try-on and simulation. And then on number 5, we're focusing on measurement and fabric verification, of course, and then the garment construction, constant refinement and patterns and avatar models. And also, to refine the product even better, we do physical try-ons. Yes, this takes us to the end of my presentation.
Thank you very much, Hamza. That was really interesting. If anybody's got any questions, I've posted in the chat that you can enter the questions into the chat on Zoom. In the meantime, I do have a question from a sustainability point of view. I was thinking about how we improve access to clothing sizes in the second-hand market, therefore enabling a circular economy in clothes. Do you have any thoughts on that one?
Come again?
It was a question about what the situation is in the second-hand market in terms of access to clothing sizes.
Hey, there's a problem. There is a serious problem, because what happens, people will buy, especially for these kind of people, they will buy clothes from retailers because they don't have choices. And then they will take it to tailors for alterations, which is a problem, especially for a complex garment like jeans. When you alter a jean, it's not the same. It's not like altering a skirt or a dress. It's like altering a man's suit, especially the jacket. for a man, because that's a complex garment. It's not easy to alter such garments. So, but they are doing it because there is no solution at the moment. Let me read this. Is the aim of the research for everyone to have bespoke measurements to encourage made-to-measure clothes rather than the mass production of clothes, and thus reduce waste, or to have a sizing system based on a larger demographic of people. If it's the latter, how does this encourage sustainability in the textile sector? For example, okay, let me go up a bit. When we say we are creating a method for bespoke, it means that whatever method that we are creating, especially for the bottom clothes, because I'm talking about the bottom one, it means whoever, it doesn't have to be a pear shape, it doesn't have to be an hourglass, but whatever person that can fit into this category, especially for bottoms, whether it's a skirt or a pant or a jean, they can use the same method, because this method calls for bespoke. When you say, and the reason why I use digital because of sustainability is because every time we use, remember when we use traditional pattern making, this and that, number one, we waste paper. When we do trials, we waste fabric. It goes to the landfill, and we know that the fashion industry is one of the biggest contributor, of that, So when we use digital, we minimize those wastage. We minimize fabric to be used for virtual try-ons. We minimize papers to be used because everything is just on the computer, and that's it. I don't know whether the question has been answered.
And then there is one more question in the chat from Alex.
Okay.
So that'll probably have to be the last one before we move on to the next speaker. But will businesses be, well, you can see the question there. It's about businesses having access to the data.
Will business be able to access the database so that they can tailor their clothes accordingly? Yes. There will be, this will be an open source like Simly 2D. Whatever that we are developing now will be open for everyone to use freely. That's the essence of this research. So we can order online, and when it comes to, it fits like a glove, there's a, okay, for this particular one, what I will do, because I'm also having a brand, I'm developing a brand as I'm doing this. What I will do online, especially now when I commercialize this research, is that whoever wants whatever a jean to be custom made for them, there will be a guide where we'll say, measure your hip, measure your waist. And then they will do that. And then automatically the system will guide you to say that this is where you fit in. But at the moment, yes, I might not answer all that because we're still going to get someone who will design that. But there will be something online as a guide, because some people don't know their sizes because there's so much confusion in the industry.
Okay, thank you very much, Hamza. That's really, really interesting talk, and great to have the Q&As as well. So if you'd like to stop sharing your screen for a second, and we can move over on to Doğuşhan, who's going to be talking about sustainable aviation fuels, very topical subject at the moment. So Doğuşhan, if you'd like to start sharing and take us away, thank you.
Hi, hello everyone. Thank you very much for the introduction. I hope you are able to hear me loud and clear and able to see the slides that I shared. Since no objection,
Yeah,
I got this as a yes.
Yeah.
Okay. So again, thank you very much for the introduction. I'm very happy to be here, present my studies to a more diverse group of people, because I usually do this for the aircraft emission community or chemistry community, but the topic sustainability brought us together. today. And my title, The Emissions Perspective, How Sustainable Are Sustainable Aviation Fuels? I know it's a little intimidating, but I'm hoping to make you feel a little better, positive after this presentation on sustainable aviation fuels. I tidied this up just to give you an idea of what I did before. Currently, I am a member of Department of Earth and Environmental Sciences and also a member of National Center for Atmospheric Science. But before coming here, I studied atmospheric chemistry and climate sciences. I started chemistry climate modeling during my master's in Bern. Then I moved to a slightly different area to see how we gather the data for the climate models, and did my PhD on aircraft emissions and their environmental impact at Paul Scherrer Institute. Then I was a postdoc for a short term studying on the dust transport and modeling, and since 2020 I'm here, and today I'm going to present you the my work that I conducted as part of being the University of Manchester. Since I mentioned about sustainable aviation, you see the first manned flight or the stamp from the first manned flight on the left, the Montgolfier brothers. And on the right, you see the design of the hydrogen-powered jet. There are a few companies now claiming that they did the first hydrogen-powered jet. Why I choose those two photos? Because, like, for me, these two are the two edges of the spectrum. On one, the first manned flight, fossil fueled one, and on the right, hydrogen only, which eliminates all the emissions monitoring. That because the emission is not a complex mixture of carbonaceous gases or particles, but just simply hydrogen under ideal conditions producing only water vapor. Simply, you can say that it's a killer for our business. But what I'm going to talk about today is somewhere in between these two. This photo is from Manchester Airport. I just took this before a flight. And based on the available technology, Sustainable Aviation Fuels, SAF, is the most feasible way to reduce carbon footprint of aviation, because you can produce SAF from various feedstock, compared to other alternative technologies or developing technologies. It's suitable for long-haul flights. But I think the biggest advantage of SAF is it enables a smoother transition compared to the disruptive implementations required by hydrogen and electric. And here you see my conservative outline, but I am going to talk about first the background, like the impact of aviation on climate and atmosphere. More specifically, what is emitted by the airliners traveling daily in the sky during different engine settings. How the SAF, the Sustainable Aviation Fuel, can help us to achieve sustainable aviation targets by 2030 and net zero by 2050. And then I will present results from field measurement campaigns that I took part here, with a specific focus on the comparison of SAF blended fuel and traditional and conventional Jet A. And finally, I'm going to discuss what these results implies for the atmosphere and what needs to be done. You see two figures here. The one on the left is one of my favorite because it tidies out all the high altitude climate impacts from an airliner, and you see the fractions of the contributions from these emissions to the global warming. So as a total, the aviation contributes 3.5% of the total artificial global warming effect, and the 36% of it comes from CO2, the greenhouse gas effect of the CO2. However, the remaining 64 comes from the non-CO2 sources. The NOx is one of the contributing gas phase emissions. It accounts up to 17%. And finally, the turbine engines, the aircraft emits particles, volatile, such as organics and sulfate, and non-volatile such as soot, which forms either impacts directly by forming contrails and cirrus clouds, or indirectly by forming the secondary particles and producing, in total, the particles also producing a positive radiative forcing. Our current scientific understanding is lowest for the particle emissions, and this is why I specifically mentioned about this particle fraction. And the highest uncertainty is especially on the volatile fraction. And it is projected that about 20 to 30 years, the aviation activity will be doubled, and this increase is also another good motivation for the stakeholders to come up with strategies to reduce these emissions. And of course, most of the time, the airline spends the activity cruising, but they also spend time at ground level. And at ground level, the source of emissions are airports. And there are more than 3,000 airports registered to International Civil Aviation Organization that is being used for commercial aviation in the world. And in the past 20 years, modeling studies have shown that the airports can impact the air quality of the neighboring residential areas. Here on the right, you see the study by Hure et al. With the particle monitors, using the mobile particle monitors, that they have shown that the particle number concentrations can be up to 4 times higher at the downwind of the Los Angeles airport by 4 times. And these emissions impacting residential areas nearby also include harmful compounds such as polyaromatic hydrocarbons. So these compounds, polyaromatic hydrocarbons, are either known or suspected carcinogens. Air transport accounts approximately 2 to 3% of the global humanity's greenhouse gas emissions, and SAF is one of the means the aviation industry is using to reduce that carbon footprint. And on average, SAF is reported to potentially reduce CO2 emissions by 80%. Compared to traditional jet fuel, this reduction is crucial to the industry's progress towards decarbonization. But the main impact of SAF lies in its life cycle, so not in the emission side. The SAF primarily uses the carbon that's part of the current carbon cycle, unlike the conventional jet fuels, which takes fossil resources out of the ground and release previous stored carbon into the atmosphere. The HEPA, let me try to pronounce this correctly. The hydroprocessed esters and fatty acids process is the currently most common and the cheaper method compared to others, simply focusing on increasing the hydrogen content of the fuel. And nowadays, we use blended, SAF blended conventional Jet A. The question is, when burned, does SAF still produce emissions similar to those emitted by the conventional fossil fuels? I am going to show results, but before going through these results, you are going to see engine power settings on the x-axis for many of the plots. So it will be percentages that you are going to see, and these percentages correspond to a specific flight mode. And this flight mode is tidied here in this figure. So if we can group them under like high altitude and ground level activities. The ground level activities is defined as a landing takeoff cycle, which consists of approach, taxi, idle, takeoff, and climb. And you see here the percentages. What these account is, for instance, for during takeoff, you need the maximum engine capacity to lift the airliner. So this is why you see 100% here, but you don't need that much when the airliner is on ground and going to a parking position. You only need 7% or less. So the cruise at high altitudes is the longest phase of flight, accounting up to 80 to 30% of the total flight time for the long haul flights. But that depends on the aircraft type, weight, cruise altitude, weather condition, and the power you need varies in between 50 to 80%. Why I specifically mentioned about these landing takeoff cycle and cruise, because like the cruise mode emissions slightly different from the LTO, which is longer and particularly important for climate, while the LTO cycle emissions are particularly important to local air quality and for the engine certification. We conducted to monitor emissions during these different engines at these different engine settings during two projects. One is the Aviator, which provided the opportunity to sample in a test cell and on wing sampling behind the parking airplane that I'm going to show some photos in a sec. And the NERC SAF at an engine test facility at Chester and provided the comparison of traditional fuel against the sustainable fuel blended Jet A. So this is the on-wing sampling that I have mentioned to you about. I put some photos for your imagination. So this is the airliner that we tested in Madrid. You see the near field probe. This is how it looks like. We bring airliner here. We park the airliner here. So you see the far field probe here, about 50 meters away from the near field probe. Why we have two probes? Because we wanted to see the evolution, the chemical or physical evolution of the plume once it is released. And here you see the far field probe. We needed a lot of material to hold it stable because these engines generate significant amount of thrust. And then what we do is near field probe, far field probe. You see they're located here. We start moving it 50 meters, 100 meters. So we're hoping to see the change in the field. So here coming to the results, you see the comparison of different seasons, Jet A and SAF. What I would like you to focus on here is the green markers. So how green markers are correlated with the others. So the x-axis in all is the engine power again, 0 to 100. So starting from near terminal ground emissions to cruise and takeoff. So we don't see a significant difference in gas phase emissions when we compare the SAF with the Jet A. So here AL to fuel ratio, this is significantly important to show that we are burning same amount of fuel to get the same amount of engine power. The CO is very similar, hydrocarbons and NOx. However, we see a reduction in the particle number and mass as a function of engine setting. Here you see this reduction in particle mass and number. It's higher at the lower thrust, but still significant during the cruising. So the burning SAF reduces non-volatile PM by mass and number, reduces the impact on the air quality. So the health effects related to the reduced air quality. It also reduces the amount of cloud condensation nuclei that is emitted, which reduces the cloud formation potential. So this is particularly important for climate. And the reason for that was we have a higher hydrogen content in the SAF that we burned. So I mentioned about the test cell. So you see how it looks like on the right. This is the scheme of the test cell we used in Madrid. The conditions at the test cell is more stable. You are not challenged by the environmental conditions such as wind speed and direction. And it's also more cost effective. You can do more tests. You can also do free tests when there are engine vibration tests or other certifications. And it's also easier to take the engine off the wing, put it up on a rack, rather than parking an airliner. And it's, you can consider the difference in the insurance costs. And the test facilities can be test beds outdoors. Here you see the cross section of one test bed in Chester, and here you see the front section that I'm going to present the results from which in a sec. And last year at this test facility, we had the opportunity to test the traditional conventional fuel Jet A and Jet A blended with SAF by half. So the mixture of Jet A and SAF, 50% Jet A, 50% SAF. And this is how it looks like. The one on the left shows the organics, the most significant fractions, the sulfate and organics of the volatile particles. If you remember, the biggest uncertainty was lying here. So here you see the SAF reduces the sulfate particles significantly, organics up to 50% based on flight mode. And it doesn't only emit gas phase, but it also particles, but also emits gas phase, which with the oxidizing capacity of atmosphere forms secondary particles. We are using horizontal oxidizing flow tubes, in which we inject ozone and water vapor to form hydroxyl radical, but like higher amounts compared to atmosphere. So we maintain a higher and fast photochemical aging inside this. Why I included this, because this is very significant at ground level. Why? Because like this is primaries for an idling aircraft at ground level, and this is the secondaries, and you see it's by folds higher by mass. So the secondary particles are much higher compared to primaries. So with different aging scales, blue is the Jet A, brown is the SAF. So different ages means like near airport, further away from the airport. And if you compare for near airport, SAF reduces secondary particles up to 80% as well, which is particularly important for air quality. So the SAF potentially reduces particulate pollution at cruise altitudes, particularly important for climate. It also improves air quality by reducing secondary particles forms, particularly important for air quality at the airport and around it. We are looking for the reasons for this impact, especially combining the particle data with the gas phase currently. And finally, all I showed you was based on the ground level tests, but how comparable are these tests to in-flight measurements? So we just got funding to conduct this research with this suite of instruments. First time in the UK, we will have the opportunity to do this next year. What we are going to do is there will be an airliner flying in front of us, and with another airliner full of our instrumentation kit in it, we are going to be chasing and trying to sample behind a flying actual airliner. We are looking forward to it, so we have a lot of work to do. But we will be working, and finally, of course, I am just the face presenting our work today, but there is a team consists of fantastic people that you see, many of them here. I won't be able to mention them by name, but I'm absolutely grateful to the Aviator and NERCSAF team. And yes, as I mentioned, there is more work to do. We need to work hard, and we will be working hard. Thank you. Let me know if you have any questions. I will be happy to answer them.
Thank you very much. That was really interesting. It's good to hear something about SAF. Really interesting research there. As I say, if you've got any questions, do put them in the chat. In the meantime, I've got a couple myself, and my first one was kind of about adaptation, really. And do you know if any major airlines are expressing interest? So it'd be quite interesting if it could actually have a financial benefit to them, and at the very least, it could have bragging rights of being the first to do it in a sort of commercial setting.
So since this is recorded and will be online, I know of them, but I to be fair, they're all in race first monitoring the impact of SAF on the emission side, and domestically in UK, the national manufacturer, engine manufacturer, tested 100% SAF already, with a charter flight company. So this we did, and there is also the CO2 and the non-CO2 specifically side is well defined in the in UK case, let's say, and there are specific calls focusing on non-CO2 projects only. So yes, both on, so to tidy this up, on engine side, we have sort of a race in making it better, or making engines ready for the SAF. We have increasing amount of SAF manufacturers and an investment to increase number of them from different sources. And I strongly recommend the UK, under UKRI domain, there is a Sustainable Aviation Fuel Cafe. They do monthly seminars from different manufacturers, like from municipal waste to agricultural waste. There are very interesting presentations that if you're interested in sustainability, it may help. And on the research side, yes, we have national initiatives. We have a Jet Zero strategy. I guess I talked a lot. I hope not, but yes, all stakeholders are on the way to reduce the carbon footprint and the impact on the environment from the aviation emissions.
That's great, thank you. There's a question in chat from Hannah asking, from the economic side, how does the cost of SAF measure up to traditional aviation fuels?
Okay, I am not the expert on this topic. I have to mention this because it's the SAF synthesis is totally another topic. But like based on the quality of the resource you use and based on the quality that you deliver. The current research suggests that it could be cheaper, even in some cases, than the traditional conventional fuel. But there will be a study, a master study on this at the engineering department, only focusing on the cradle to that sort of cost comparison of Jet A and the sustainable aviation fuel. So I hopefully next year, both on emission side and on the cost side, I will be able to present these results.
That'd be really interesting to see that, especially if there are benefits economically, that could be really helpful. Yeah, we've probably isn't there any more questions in chat, but I'm just going to ask a bit of a nerdy question. Really, is there any way this sort of fuel can be used in propeller planes for really small, sort of short hop flights, where there's kind of a big impact on, presumably a big impact on the low on the ground level? Thinking of really small sort of propeller planes.
So they are more similar to the propeller planes are, let's say, more similar to the helicopters. And there is a very recent study which did this work with 100% SAF. So I based on these results, I can suggest that it reduces both climate. It's an improvement to both climate and air quality sites. And I think the only, my perception, I'm not a mechanical engineer, but like my perception is the only challenge is to provide SAF, enough SAF currently to the engines that we already have. I guess the transition is already done for most of the long haul flights. And I mean, since there is this helicopter example, I am quite positive that that could be a case for the propeller flights.
Brilliant. Thank you. That's really interesting. So thanks again for answering those questions and for your talk. I think we can, since we've got no more questions, you've satisfied everybody, and we can probably come towards a conclusion. So thanks again to both of our speakers. We will be having another one of these, I think probably in the new year, but don't quote me on that. But we are always looking out for new people to present at our seminar series, and we've got a few dates in your diary for the next few months, of the next month at least. We have an early career research and networking and mince pies, and I think that also mulled wine event on the 4th of December from 3 till 4:30. The details for that are on the Eventbrite. That's in the Henry Royce building on campus. So it'll be a kind of in-person get-together to discuss some ideas around sustainability and eat pies. What more could you want for Christmas? And then also on the 12th of December, we've got a one of our big Sustainable Futures events, which is celebrating a disciplinary research, sustainability research at the Alliance Manchester Business School. Again, the details are on Eventbrite. And then in the new year, on the 23rd of January, we've got our annual big prestigious lecture, which is the Albatross Lecture, again at the Business School, with Dr. Jared Mogulis talking about the illicit trade in plants, which will be really interesting. Again, Eventbrite for all those details. And I think there are drinks and networking after that as well. So that should be really good. Yeah, so thank you everyone for coming. Thank you to our speakers. Details are in the chat as well. Thank you, Alex, for posting those.
Just one thing I forgot to put any contact information to the slides. If there's anyone who has any further questions or any other questions, please feel free to contact me. I just posted down there. Sorry for the interruption. Thank you very much.
Oh, that's awesome. Thank you. Yeah, the email address is there and also LinkedIn profile. So yeah, that would be really good to follow you up with some of those things. Really, like I say, really interesting research. So thank you everybody for coming, and I'll see you at the next one. If not, have a Merry Christmas. I'm the first person to say it of the season. Bye.